Hello everyone, it's Salar and we are in part 34 of our tutorial, a tutorial to writing a real-time operating system. From two parts ago, I started to talk about interrupt and exception, and in this part, as a part 3, I want to close this topic. And in this part, I want to give you some information, interrupt and exception, and returning from interrupt and exception, and nested interrupt and priority in interrupt. Okay, so let's jump to our business. Before talking about nested interrupt and priority, I want to give you some information about pendency interrupt because I want to talk about priority. To talk about priority, we need to have at least two interrupt handler in our program. From previous parts, for example, we have sysdig handler in program. And as another example, I want to give you some information about pendency. I will give you a lot of information about supervisor exceptions and system call in ARM processor, but in this part I want to just give you little information about this interrupt to use that to describe interrupt priority. Okay, pendency is one of the exceptions core interrupts in ARM that can be utilized in OS development. Okay, but if you want to activate this interrupt and jump to interrupt, you can use this line of code by software and writing a 1 in ICSR register bit 28, writing a 1 to this bit. By software you can jump to this interrupt. So let's show this interrupt in Eclipse. Okay, this is the example, and I want to jump to this handler by running this line of code. The symbol of pendency handler here is in startup code in vector table. Okay, so let's run this line of code in assembly form. So with this store instruction, if you run this instruction first, your processor jump to next instruction but doesn't run this instruction. If you another time run next, your processor jump to pendency handler. Okay, so by software, by writing 1 in bit 28 of this register, you can jump to pendency handler. Very good. Let's go back to our slide. But as I said, in this part I want to talk about interrupt and exception returning from interrupt and exceptions. As I said, in assembly programming and function call, when you jump to a function, your processor write return address in link register, and at the end of all of your functions, compiled function, you have a bx branch and exchange with link register, and with this instruction your processor write return address to PC. Link register to PC and return to the caller function. But when you have an interrupt request, your processor write this value in link register and do a stacking, write and push these registers and return address in the stack, as I said in previous part. And at the end of the handler, when you want to return to thread mode, because in link register you have this value, your processor do unstacking. Okay, your processor do unstacking. Write these values from a stack to its registers and write return address to PC and return to thread mode. Okay, so because at the end of all of compiled function, C compiled function, you have this instruction, you can use all of your function as an interrupt handler. Okay, because of this facility and stacking, you can use all of your function, C function, as an interrupt handler. Very good. But let's talk about nested interrupts and priority. Each interrupt in ARM processor, each interrupt and exception in ARM processor has a priority. Okay, so for example, assume that you are in an interrupt and at the middle of this interrupt, for example in this point, okay, in this point you have an interrupt request, but requested interrupt has higher priority. Your processor stop running this handler, jump to interrupt with higher priority, jump to this handler, run this interrupt handler to the end and return to the interrupt with lower priority. Okay, and run the rest of instructions in this handler, and after that return to thread mode. Okay, so interrupt with higher priority preempts the interrupt with lower priority. In this time, your processor stopped running this interrupt, run interrupt with higher priority. After running this interrupt, return to interrupt with lower priority to this interrupt. But assume that you have an interrupt that are running with a higher priority, okay, with a priority, okay, with priority. For example, assume that here is time frame, and in this time, for example here, you have an interrupt request with lower priority or same priority than this priority. Because this priority has higher priority or same priority, your processor run this interrupt to the end, return to thread mode, another time jump to this interrupt. Okay, so for this scenario and this scenario, let's give you some information and let's give you some example for these two forms in Eclipse. Sorry, before see the examples, let's give you more information about priority. We want to change the priority of interrupts before seeing the example. Assume, for example, in Cortex M7. Okay, in Cortex M7 there are maximum 256 levels of priority. Okay, from 0 to 255. 0 has interrupt with 0 priority has highest priority, and interrupt with 255 in Cortex M7 has lowest priority. So smaller number has more priority. But except these levels of priority, we have three other levels of priority: -3, -2, and -1. Priority of reset, non-maskable interrupt, and hard fault handler. Priority of these exceptions are unchangeable, and you can change the priority of this instruction. But for example, you can give to SysTick a priority, for example 258. okay, or for example 10, or for example 0, or other numbers between 0 to 255. But you can change the priority of reset, non-maskable interrupt, exception, and hard fault. So with 256 levels of interrupt priority and these three levels, we have 259 levels of priority. Minus 3 is highest priority, 255 is lowest priority in ARM Cortex M7 standard. But a designer, an SoC designer or microcontroller designer can design a microcontroller with Cortex M7 core with fewer levels of priority. For example, my microcontroller STM32F764, or for example this microcontroller from NXP, just have 16 levels of priority, a subset of all of these levels. Okay, for example, in these microcontrollers, just 16 levels implemented. But at the reset and after reset, all of interrupts has priority 0, except these exceptions. Okay, because priorities of these exceptions are constant. Okay, but how can I change the priority of an interrupt? For example, system tick. With this CMSIS function, you can change the level of priority. For example, in my microcontroller, the levels of priority is from 0 to 50. Here is highest priority and here is lowest priority. Okay? If I want to change the priority of system tick to lowest priority, I can run this function. Okay, the CMSIS function. But before using this function, I need to change this value in CMSIS code. What's this value? As I said, my microcontroller has 16 levels of priority. You need to put number 4 in this definition, because to the power of this definition, for example, x is the number of priority levels. For example, in microcontroller 60, so x equal to 4. So I need put 4 in this definition. Now let's see the example in Eclipse. So here is example, but before talking about this example, I said to need to change this number according to your microcontroller. For example, for microcontroller to 4. Okay, and save that. But let's to inspect this example. As I said, to talking about priority, I need at least 2 interrupt handler. Now PSP handler and system tick handler. First config system tick handler, after that changing the priority of these handlers and these interrupts and exceptions. Now in my example, in first example, system tick has lower priority because bigger number than PSP. So let's run this code. So let's run the code to the system tick handler. Now I'm in system tick handler and I want to have an interrupt request to PSP, but because system tick handler has a lower priority, like this example at the middle, for example, assume that here is systic, here is pen this v with higher priority. Another time here is systemic, because systemic has lower priority. When you have an interrupt with higher priority at the middle of your handler, your processor jump to interrupt with higher priority. So when you run this code, your processor does not run this line of code and jump to systemic handler. Okay, run this function to the end, and another time return to this line and run systemic handler. After that, return to thread mode. After that, return to thread mode. But let's to change the priority of systemic and pendency. Now here has higher priority. Now systemic has higher priority. Let's do run my code. So run to the systemic handler and interrupt request to the pendency. But because systemic handler has more priority, your processor run this handler to the end. To the end. Okay? Return to thread mode. Run interrupt to the end, return to thread mode. Another time jump to interrupt with lower priority. Another that. Jump to pendency handler. Run this handler to the end, and another time jump to the thread mode. Okay, so let's do back to our slides. Okay, here was some information, example about nested interrupts and interrupt priority in ARM processor. You can find other information about interrupt priorities, for example, about priority grouping. Okay, you can find more information, for example, about priority grouping in technical reference manual of your processor. Okay, but I don't want to talk about interrupt grouping in this topic. Okay, you can find a lot of information about that on the internet or documentation. So as I said, when you jump from a thread to an interrupt handler, your processor write this value to link register, and it means you are in an interrupt handler. But when you are in an interrupt handler and your processor jump to another interrupt handler with higher priority, your processor write this value to link register. Okay, this value to link register. And it means that you need to do unstacking after returning from this interrupt, and another time jump to handler mode. Okay, so let's see an example. Another time change the priority of this interrupts, and another time systemic has lower priority. Make the project and run the debugger. And run the code to the systemic handler. As you can see, when you are in your handler, you have this value in the link register. But if you jump from a handler to another handler, now you have the value of F1. Okay, another time return to systemic handler, I have F9, and another time jump to thread mode and I have some value in link register. Okay, very good. But in another scenario, if second interrupt has same or lower priority, your processor return to thread mode, another time jump to handler mode, and another time in link register you have this value with F9, like this interrupt, because your processor went to this handler from thread mode. Okay, and let's to talk about stack pointer, and let's to give you more information about a stack pointer in ARM architecture and ARM processors and Cortex-M processors. As I said in previous parts, when I talked about stack and stack pointer, I said that you have a stack pointer register R13, but actually you have two stack pointer, main stack pointer and process stack pointer. Okay, and at the moment just one of them is active. Okay, at the moment just one of them is active. Okay, after reset, when you are in thread mode, your processor use main stack pointer as an stack pointer, so your register R13 is main stack pointer. But you can change your stack pointer to process stack pointer by changing this bit in control register to 1. You can use process stack pointer when you want to develop an operating system. I will give you a lot of information about process stack pointer in future parts when I want to talk about process in processor. Okay, but in this time, when you are in thread mode, you can change your stack pointer from main stack pointer to process stack pointer. In this state, R13 is process stack pointer, but in handler mode, your processor always use main stack pointer. But how can I use process stack pointer? Because to talk about activating process stack pointer, let's give you some information about process stack space. As I said in previous part, at the end of your SRAM, you have a stack space, but this is main stack. Okay, main stack space, and here is main stack pointer. If you want to change your stack space to process stack space by changing this bit in control register, you need to allocate space to your process stack. For example, here I want to allocate an space to process stack from heap. Here is my heap from end to heap limit. Okay, with this code example, you can allocate a space to your process stack before changing the stack pointer. For example, assume that I want to have a process stack with this size. With malloc, you can allocate this block in your heap memory, and after that, the address of first byte in your process stack plus process stack size is process stack top. Okay, you can have process stack top at the end of your process stack and use that in process stack pointer. Okay, but let's see this example in Eclipse. See this example. Before to changing stack pointer to process stack pointer, I need to allocate space to process a stack. For example, here in my example, 1 kilobyte in my heap memory. I want to allocate this space in heap memory. A block in heap memory with this size, process stack size, another time plus process stack size is process stack top. Process stack top end of this space. Okay? And put this value in process stack pointer. And after that, change the process stack pointer. But let's change this example. Assume that here I have solar function. I want to jump to solar function. Okay. Assume that here is my example. Change my example. Okay. So let's debug this example. So in my register bank, I have stack pointer register, and I have main stack pointer and process stack pointer. Main stack pointer, process stack pointer. The value of stack pointer after reset is value of main stack pointer. Okay. So now my processor is using main stack pointer, but by running these lines of code, I can put a value in process stack pointer and allocate process stack in my heap memory. Okay, now here is my process stack pointer, but now the stack pointer is main stack pointer. Now by this line of codes, I can change my stack pointer to process stack pointer. Now the value of my stack pointer is value of process stack pointer, CE0. CE0. Now in this time, if I jump to a function, for example solar function, my processor using process stack pointer. Okay, process stack pointer. Or if another time return from this function, now I have my process stack top in process stack pointer. So in this way you can use process stack pointer. But what is the application of process stack pointer? I will give you a lot of information in future parts. But let's do back to our slides. So here is stack pointer. In thread mode, you can use main stack pointer or process stack pointer. But let's talk about handler. Okay, when you are in thread mode and you are using PSP as a stack pointer, if you jump to handler or jump to an interrupt, your processor use process stack space to do stacking and put this value FD, not F9, okay? Put FD in link register, and in handler mode using main stack pointer, not process stack pointer. And to return to thread mode, use another time process stack pointer to do unstacking. Okay, because LR is FD, and another time return to process stack pointer. So now let's see another example. And in this time, let's change this function like before. And this Control V and jump to pen this handler in this line, but ICS our register right in between 8. Okay, now let's talk about process stack pointer and interrupt handlers. Okay, and handlers. So debug this project. Okay, now let's first change the stack pointer to process stack pointer. As you can see, the value of stack pointer is value of process stack pointer. Okay, let's do C assembly code. Jump to link register. Now if you jump to pen this handler, okay, now as you can see, the value of process stack pointer is CE. Okay, remember this number. If you jump to pen this handler, now I'm in pen this handler, I'm in handler mode, and my processor used have used PSP to do stacking CE0 now to CC0. Okay, PSP has been changed, but in stack pointer I have the value of main stack pointer. Okay, because in a handler your processor using main stack pointer. So if you do this stack operation, stack instruction, your processor write the stack in the main stack pointer. As you can see in handler, your processor changed the value of main stack pointer. But if you another time return to thread mode, your processor using value of process stack pointer as the stack pointer. Okay, here was some information about process stack pointer and interrupt and exception handlers. Let's do return to our slides. As I said, when you are using process stack pointer, use process stack space to do stacking, but in handler mode use main stack pointer. Another time in thread mode, after returning, use process stack pointer. Okay, but when you have an interrupt with higher priority, after this interrupt, here use handler MSP, use main stack pointer for this stacking. Another time handler MSP, use MSP to do this unstacking because here is F1, and another time in this time because here I have FD, use PSP to do unstacking. Okay, here use MSP to unstacking, but here use PSP. Here use MSP to stacking, but here use PSP. Okay, but here is more information about link register. For example, in bit 2, in bit 2 in this value, bit number 2, return the thread stack. Okay, for example, here FD means that you are using PSP, so bit 2 is 1. Okay, or for example, bit 3 shows that you want to return to thread mode or handler mode. Okay, for example, here you want to return to handler mode, or for example, here you want to return to thread mode. Or for example, bit 4 shows you are using floating point unit or not. I've never used floating point in my examples in this tutorial, so this value is 1 for me. And other bits from 31 to 5, not 25, to 5 is 1. Okay, here is more information about link register, and these 2 bits are reserved. Here is 1 and here is 0 and here is 1. Okay, so these slides were some information about interrupt, return, exception return, and stack pointer in interrupt handlers and in threads, and some information about priority and nested interrupts. Here is enough to talking about interrupt and exception in ARM processor, and in next part I will start to talk about operating system, real-time operating system. Finally, in next part I want to talk about real-time operating system and what is real-time operating system. So very good, thank you very much to see me, and see you soon in the next part.